programming. This time I will complement the last episode, in which there is one topic missing, and it's the topic of signs and unsigned types in general, because I've mentioned specifically signs for the float type and the double type, but it's also important for types that don't have the floating point notation, like the int type and the char type. You have the unsigned version of int, that's the unsigned int. In unsigned types, you have that, for example, if you have the value 1, it's represented exactly like 1 in binary with the amount of bytes that the type has. Like unsigned int has 4 bytes, the value 1 in unsigned int will be represented in the machine as 4 bytes of binary 1. That means 1 byte of only zeros, another byte of only zeros, another byte of only zeros, and finally 1 byte that finishes in 1. And so 2 will be 2 in binary, 100 will be 100 in binary. You get the idea. But that's not the case if you want to have negative values. And typically you represent the negative values using the complement of 2 algorithm. That is, if you have a positive value, the negative version will be 2 to the power of the variable length minus the positive value. That means the positive version and the negative version will sum 2 to the power of the variable length. So if you visualize the binary number, you have to flip its bits and sum 1. You can think of that as, if you have a binary value, the 2 to the power of the length binary number will be 1 and 0, 0, 0, 0 to the end of the binary length plus 1 of the value that you are originally thinking of. So that's the way we represent them. It's not just that you put 1 or 0 in the front of the value. You have to actually calculate, and that is made to make some operations easier, like you can make subtraction by using the sum circuit. And that being said, I guess that's what was missing on the last episode. But now we must test it. There's this curious experiment here, that you have unsigned char and you have the char. So we would have that sign concern, but the chars are only represented in principle by that ASCII table. So in both cases, if you print it, note that it isn't the correct way to print a char. you are printing it as an integer. So if you print it as you will print an integer, you have always the decimal version of the binary raw value of that variable, that in the case has 1 byte. So you can test it here and see. And that's it. Always remember to break your lines. No big deal. So you can see. Remember that this variable is an a that you incremented, and the incremented is reflected by the ASCII value of a plus 1. That's b, as we already tested here, a and b. So let's make one more experiment, like let's say that we have, now let's reuse that x variable. We were talking about sign, so let's put -2 and let's try to print that. Now that's when we play with unsigned values. We have that y unsigned that, and let's see what happens if we might just get an error here. Let me just say that I'm aware of that. But let's just try to see how insecure C can be. By the way, the correct way to print this in this case is with the %u for the unsigned int. So let's go there. And there you have it. So you have that but anyway, there's one more fun thing that you could just do, right? But let's talk about this now. You have naturally the -2 value, and you have, it just puts in the unsigned variable, and you print it like an unsigned. So you have the decimal conversion of the raw binary representation of -2. That's like this. use for bytes. The last thing is, what if instead of we can't go to y, what if we just play around with the way to output the variable? Let's see if it will just display the same thing that we have seen in y, because it's displaying in an unsigned way now. That's it. X is -2, but X is also this value if it's read as an unsigned variable. That's interesting to show how this computer science topics depend on how the user reads the results. So that's it. Once again, I'm delaying the topic. Next time I should talk about branches and loops. See you in the next episode.